Let me start with different types of precipitation. First is liquid precipitation. That could be rain, which light or heavy, different intensities, or snow, drizzle, hail, and there are many other names. I once was at the University of Aberdeen, that's in the east of Scotland, and I think they have out of 365 days a year, 364 days of rainfall or something. Almost, you know, not as bad, but very frequent rain. And they have a lot of, it's not so much, it's very light rainfall, usually some drizzle, and they have all sorts of different Scottish names for that, for all these different intensities of precipitation. We would just call it drizzle, but because they're very experienced with it, though they have all sorts of local names, quite interesting. And maybe you come from other regions of the world where you also have many other names to characterize the local precipitation. Some pictures again, snow. Very difficult to take pictures of, but you see it here in the intercepted snow storage on these trees here, or some rainfall. Also very difficult to take pictures actually when it's raining, but you think that you see that there's some rain probably down here, yeah, and here only clouds, but you can see the rain over there. Some intercepted precipitation. It could be solid or liquid. Liquid intercepted precipitation here on the spider web. You see here beautiful drops, and then solid could be snow or ice around some vegetation in these cases. Yeah. This is intercepted precipitation. Well, you see here the direction of it. You see exactly from which direction the wind is blowing. You see that? From that side to that side, I think. Left, right. Yes, I agree. From left to the right. There was, we talked about the water balance equation earlier today, and you say usually it's rainfall, it's runoff, and evaporation. Yeah, and in the Canadian prairies, do you have somebody from Canada in the room, or no? It's in the prairies. That's between the Rocky Mountains and eastwards. There's so much. It's pretty flat topography, and very semi-arid, but cold. It's cold and dry. Yeah, 300-400 millimeters of rainfall, and there more water is leaving the catchment via wind drift than discharge. You have so strong rains and so much wind drift of snow and ice that more water is leaving the catchment via the wind than doing the discharge. You can see this can also impact the water balance equation. Huh? In most other catchments where you don't have this, like in the Canadian prairies, maybe this is negligible. But I found it very interesting that they quantified that. Good. These were different types of precipitation. Let's look at precipitation formation processes. Oops. Wrong direction. First, it's from water vapor in the atmosphere. Nothing new here. We have water vapor in the atmosphere. How does the water vapor get there? You need to have rises of air masses with moisture. Yeah, when they go up, they expand, yeah, and cool. So the moisture is cooled down. It's getting cooler the higher you are. And if you have temperature below a certain threshold, discuss that threshold in a minute, you have less and less water can be held, and then there's condensation. Yeah, and the condensation usually needs some. It always needs some aerosols. These are small particles where the condensation happens, and around these aerosols you have small drops or ice crystals. Yeah? So the air with moisture, with water gas, water vapor, moves up. It gets cooler there, cooler. Then it starts with condensation. That means it goes from the gas phase, water vapor, to liquid or solid water. Huh? Liquid is a raindrop. Solid is an ice crystal, for instance, yeah, or snow crystal. And these then get bigger and bigger. They get heavy enough, yeah. And if the raindrop is big enough that that gravity cannot hold it anymore, so the drop is increasing, then it's heavy enough, then it falls down again. Is that clear? Good. That's what I say here. Excess of water forms droplets, mainly in light clouds, or ice crystals that's needed for real precipitation. When you want to have some real rainfall, it needs to go through the ice phase. So water in the atmosphere only in clouds with vapor, with liquid, with drops, usually does not make any real rainfall. So it's a bit of drizzle maybe, but the real heavy precipitation has gone through the ice phase. Yeah, so it was so cold that the droplets were frozen and you had ice before. But they need to get large enough that they also fall down. So the water goes up, goes up, goes up, forms a drop, forms an ice crystal. This ice crystal is growing, 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 and then it gets too heavy, and then it cannot hold in the atmosphere, and it falls down. Gravity brings it down. That's then the precipitation. When the ice crystal on its way down, again, the atmosphere is getting warmer. When the ice crystal falls down, melts. So then we at the Earth, at the surface, we experience rainfall. But it was ice before, but it's just melting on the way down. Yeah? Is that clear to everybody? I hope so. That's the rainfall formation, roughly, briefly summarized. And that's true for all further rainfall formation processes. This is always true. Yeah? You need to internalize that and think it through yourself tonight or tomorrow or whenever. Yeah? Then we have a so-called lapse rate. The lapse rate is the cooling with height or with elevation. The higher, the cooler. Usually it's on average 6.5 degrees or Kelvin, same as degrees Celsius in the absolute range, per 100 meters. Maybe you experience that if you walk up a mountain, it's always cooler on top. Huh? On an average, it's 0.65 Kelvin per 100 meters. There's also a difference between wet and dry adiabatic gradient. So these are two different gradients which I will explain in a minute. But generally, it's getting cooler. There's less pressure. The higher you are, that leads to an expansion of the air and therefore a cooler temperature the higher you are. Yeah, temperature fall. This lapse rate is important. Let's look at water vapor pressure. Maybe might be a déjà vu from your secondary or bachelor physics lectures which you had before. We speak about the vapor pressure in the gas phase. It's the H2O, also the partial pressure, is also called the vapor pressure. So in a box with air, what do we have? Don't read it. What do we have in a certain volume of air? What do we have in this volume of air? What? Gases. Different gases. Yeah. What are the main gases? The main is nitrogen. Yeah, it's 78% or something. Huh? Then second is oxygen. 21% oxygen. Yeah. Here a bit less, I feel at the moment. So. Carbon dioxide. Yeah, I'm breathing. Yeah, I'm burning carbon and breathing. So carbon dioxide, of course, very variable in space and time. What else? What else is in the air? I couldn't. A little bit of halogens. Halogens. Oh, that's what I said. Yeah. True. Yeah, and noble gases, argon is a bit less than 1% usually, 0.9 something, and then could be helium or whatever, huh? Different noble gases. True. And now we are doing business, huh? H2O. And the amount of H2O in that box of water is expressed with the partial pressure of H2O, the water vapor. Yeah? Vapor pressure. It's expressed usually in Pascal. In these units, you see there, and we also have different units for Pascal. I think this is basic physics. You can look that up in the textbook yourself. But important is that we have per volume different water vapor pressure depending on the H2O molecules. If we have too many H2O molecules in a given volume, let's say 1 cubic meter of air, yeah, if you have too many, then it starts with condensation. Yeah. The amount of H2O molecules that can be held as gas is temperature dependent. The warmer the air, the more H2O can be held in the gas phase as water vapor. If you cool that air, cooler, 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 then at a certain threshold it exceeds the so-called dew point. That means it starts with condensation. Yeah? You see that in the early morning, it was very cold in the night. In the evening, all windows of a car were completely clean. In the early morning, they are wet. What is that? Condensation of water. The air was warm in the evening. During the night, it cooled down. It exceeded that dew point. It started with condensation, and then the H2O molecules condense wherever they can. In this case, at the window, at your window of your room, or at a car somewhere. Yeah, usually they prefer these type of surfaces. And the same is happening in the cloud formation. You have temperature 20 degrees, then there's a certain amount of water vapor in that volume. Then you cool that air, you cool it down by moving the air up. Then the dew point is exceeded. That means it's cooler than that all H2O molecules can be kept as water vapor, as damp, and there's condensation starts. So the cooler it gets, then it starts with condensation, and some of the H2O molecules now become liquid water. Yeah, that's the so-called dew point at that change. Is that clear? Good. Here you see that's the most important equation for today. No, this is of course the most important equation, the water balance equation, but for the rest of the day. That's the saturation vapor pressure temperature relationship. What do you see here? This is the temperature, 0 degree up to 30 degree, and you see here water vapor saturation. And air, a box with air, a volume with air, yeah, of 10 degrees can hold 1.3 or what is that, kilopascal water vapor. If the amount of H2O molecules expressed to the water vapor pressure is below 1.3 at 10 degrees, then it's under saturated. That means it is not 100% saturated, that air. That could keep even more H2O molecules in as water vapor. If the water vapor pressure is above 1.3 at 10 degrees Celsius, then it's supersaturated. That means there is more water vapor than actually the air can hold as water vapor, so condensation would start. Yeah? Immediately when you go above this line, supersaturation usually hardly happens in a big scale in reality, therefore saturation would start. Yeah? So here we talk about unsaturated water vapor, and here above saturated. This air here, what do you think? Is that saturated or unsaturated? Unsaturated. Otherwise we all would have some fog on our glasses here. Huh? Yeah? It's maybe here's a humidity of 75% or so, I don't know, but I guess. Yeah, that means from this air, maybe 23 degree warm here in this room. Yeah? That's the temperature. 23. Just make 25. That's easier to read. Huh? 25 degrees. So the water vapor that can be held as water vapor in this atmosphere, in this room, would be a water vapor pressure of 3.2. Yeah, but maybe it's not 3.2. It's maybe 2.0. I'm just guessing. That would mean 60-something% water vapor pressure in this room. Yeah? If it's above 90%, and it starts to get humid, and you feel like it's uncomfortable. Yeah, because you cannot transpire so much water anymore because you are reaching saturation. Is that clear? You are so smart, because I needed forever to understand this. Well, it's very good. We express this line. We express this line with the Claudius-Clapeyron relationship. These were two scientists that found out about that, and it's an exponential function, temperature dependent, like this. Yeah, you can type that in your calculator, or in your telephone, or in your Excel sheet, or you look that up in water pressure tables. That's also in every textbook. You find these vapor pressure tables where you can look it up. This is exactly the same equation. Let's play a little bit with these different numbers. We have air temperature of 35 degrees, so we are here. Maximum water vapor pressure would be 5.5 roughly kilopascal. You agree? Yeah. if now the water vapor pressure is only 1.5, so we are here, then this, what is this then? That's the saturation water vapor pressure deficit. So this amount of water could still be held in the atmosphere. Yeah? That's the deficit. Yeah? If the water pressure is up here, then we talk about saturation. Clear? What happens now if our temperature here, our nice air volume 35 degrees, somewhere in the tropics, water vapor vapor pressure 1.5. Now we cool it down. Maybe here the total the total humidity, so that's percentage of the total air that can be held as water pressure, is only 30%. Now we cool it down to 30%. To 30 degrees, excuse me. The water vapor pressure is maybe not 30%, it's now 35 or 40%. We cool it down to 20%, to 20 degrees. Now the water vapor pressure is already 60, 70%. Yeah? We cool it down to 14 degrees. What is now? 100%. That means at this 14 degrees, the so-called dew point is exceeded. That means we have 100% humidity, 100% of the water vapor that can be held as water gas is now water vapor at this point. That's the dew point. If we cool this air below 14%, condensation happens. So we stay on this line now, and more water vapor would leave as water vapor and be condensed. Is that clear? Some of you look at me if I'm not so clear. Talking from another planet. Okay, try again. You have a volume of air. Think about one box of air, 35 degrees warm. A humidity of 30%, that means it could hold 5.6 or 5.5 vapor pressure. It could have that, but it only has 1.5. So it's only humidity of some 30%, roughly, bit less. Huh? Now we cool this air down from 35 degrees to 30 to 20 to 14 degrees. Yeah? And at 14 degrees it reaches 100%. That means now we have 100% saturation in the air, yeah, at this point. And that's the so-called dew point. Then dew starts to happen. That's exactly what happens in the morning. You get out of your room and it was cold last night and all the windows have dew. Yeah, there the condensation point was exceeded last night. It cooled down so much that the air could not hold the water vapor as vapor anymore, and it's now condensated to some surfaces like leaves or windows or yourself maybe or whatever. Yeah, that's the dew point. The amount that is not saturated we call saturation vapor pressure deficit, because this is unsaturated. Yeah. The saturated vapor pressure ES is this point. For a given temperature, this changes along this line. And the dew point is a temperature when the water vapor pressure has exactly 100%. Yeah? Tried now 2 times to explain it. I think that was a long day for you as well. For the people who didn't get it immediately, I strongly recommend to read that up and again in the course notes, also explained there. Yeah?
I have a question.
Yes, please.
So it's look like air conditioning. If you have the humid air in the air conditioning is working, it's putting pressure on the and bringing the temperature down, and the water is just coming out.
Yeah. Did you get his question? Excellent question. Maybe you pose it again that all your colleagues understand.
I say that if in a room with air conditions are working, so there is a humidity in the room, and the air has a moisture inside, and the air conditions suck that moisture, and the compressor put pressure on the air, and it's the liquid at the end of the dew points, or the water is coming from the other end of the
Yeah, excellent. What do you think? Is it pressure what the air conditioned system doing, or just cooling? It's cooling. Yeah, it's cooling down the air. Then the dew point is exceeded. It's cooling so much that the air cannot hold the H2O molecules as vapor anymore, so it's cooling, dew is happening, it's starting raining below your air conditioning system, and if it's not well not well done at least, and the cold air that is discharged from your air conditioning system is then much drier. Yeah, so you filter out, you could say, through temperature. Filter is the wrong word. So through temperature, you condense out H2O molecules. Exactly. Yeah. That's what the air conditioning system is doing. Yeah. Clear to everybody? Good.
This looks like a psychometric test, part of a psychometric test. But is it possible to have, because on the psychometric part, there's the pressure part, the humidity axis. Is it possible to have two different charts for probably two regions? Because
you mean different geographic regions?
Is there a standard chart for even the temperature and pressure?
This is the standard chart. This is pure physics. It has nothing to do with different regions of the world. Of course, the temperature is much higher in the tropics than in the temperate zone, but this is true always. This is a general law.
Because I saw two charts somewhere, and they stated something below, like a legend, that something for a region, something, and well, it's not just this. It's like a psychometric chart that defines algae and everything together.
Yeah, maybe you can bring it on Friday if you find that chart again. But I don't know exactly how that looks like. I cannot comment on it. But this is true everywhere. Of course, it's much higher. You start at much higher temperature in humitropics than in temperate or cold climates. That's for sure. But this is universally true. Yeah. Yes, please.
For a higher temperature, it will require us a lot of water in quantity to get that dew point.
Yes, absolutely. The higher the temperature, the larger the holding capacity of the water vapor. Absolutely right. Yes. That's what this exponential function is showing. Huh? The warmer the air, the more water can be held as water vapor. Yep, absolutely. Good. So read that again. But this is the basis to understand humidity and the basis to understand rainfall generation. So we have to understand this. Good. Couple of words properly defined, which I used before. We talk about vapor pressure. That's the partial pressure of H2O molecules vapor in the air. Humidity, that's the pressure we have divided by the total pressure times 100%. The saturated pressure. Yeah. Then we talk about humidity. I said 30%, 60%, and so on. Yeah. 100% humidity means ES and ED and ES are the same. If that is then the point if the vapor pressure deficit is 0. So if these are the two same values, then this becomes 0. The vapor deficit is 0, and then the humidity becomes 100%. Yeah. The dew point is a temperature. It's not a pressure, it's a temperature. The dew point is a temperature at which air at a given water vapor pressure would be saturated. Yeah. And you can compute this by using this equation or some tables which you can look up in textbooks. In the exams, of course, we would give you tables to look up or the equation or whatever. Yeah. Here are some calculations for you for tonight, after supper, you know. Now then you can play with some numbers and calculate this for you to exercise that a little bit. You know, in the evening, temperature drops below 16 degrees. What is the humidity and all this? These are simple applications of that term. I'm not sure if Dr. Laat makes a separate exercise on this, but yeah, you can find it also. There's another exercise, and as a nice person as I am, I give you even the solution of this. But you can play at home with a calculator if you get the same numbers. Now we have I talked about lapse rates. What is a lapse rate again? That's how the gradient of how cooler it gets with elevation. We said on average 0.65 degree or Kelvin per 100 meters. Yeah. Now we have a so-called dry adiabatic and wet adiabatic lapse rate. That's all. I don't want you to understand this. We do that later. But only the dry and wet or saturated adiabatic. Dry is a very steep gradient. Usually, now it is physically 0.98 degree per 100 meters. So say 1 degree per 100 meters. So if your humidity is not 100% and you walk up a mountain, which is 1 kilometer higher than you are at 500 meters and you walk up the mountain to 1500 meters, then how much cooler is it up there? Stable temperature. It's 1 degree per 100 meters, so if you walk up 1000 meters, it's 10 degrees colder. Yeah? Is that clear? Yeah, 1 degree per 100 meter. Now, there's a certain point when it's getting cooler, and maybe at say 1200 meters, you reach a temperature which is the dew point. So what would that mean? That means if it gets cooler, there is condensation happening. Yeah? So you walk from 500 meters to 1200 meters, 1 degree cooler per 100 meters. Now at 1200 meters you reach the so-called dew point. That dew point means that some of the H2O molecules now change the phase from water vapor, from gas, to liquid, condensation. Yeah? What is happening? So the energy of the gas status is changing from gas to liquid. What does that mean in energy balance? So that some of the temperature cooling is now start the sentence differently, sorry, it's also late for me. That if now condensation is happening, that some of the cooling energy will be covered up by this condensation of water. So you need by lowering the energy phase from gas to liquid, you give energy to that water, to that volume of air. So then the cooling is not 1 degree per 100 meters anymore. It's maybe only 0.5 degree per 100 meters. Yeah. After the dew point, the gradient is different because of the change of the gas to liquid gives energy free. Yeah. You bring the H2O molecules to a low energy status, therefore they give away energy. Does that explain simpler one up? That's what you see here. The black line for a moment. Dry adiabatic conditions. So you go up with altitude 1 degree per 100 meters, and then here's the dew point and 100% humidity. If you go up further, the change of temperature condition is only 0.5 or 0.6 degree per 100 meters. It's because of the condensation of H2O molecules. You also, if you fly next time, look out of the window. Yeah, you see sometimes you go up and you see clouds, and sometimes the clouds have a very sharp lower boundary. Have you seen that? They look like cut. Somebody with a knife cut at these clouds. What is that? That's exactly the elevation when the dew point is reached. Yeah, below unsaturated air, above saturated air, and exactly at this. We look at some pictures later. Exactly at this elevation, condensation starts. Yeah? Believe me, I'll show you some pictures. Nah. Can you see this? Hope you can see this here. It's a pretty straight line here, the lower line of these clouds. Hope you can see that. Yeah? Here, unsaturated air conditions, and if you go up, cloud formation starts and saturated air conditions. You have a better picture of this. Here, you see this? Looks like these clouds are cut with a knife, huh? This is the elevation of the dew point. Yeah? Here? Ah, wait a minute. Good. So we said there are the dry and a wet adiabatic temperature gradient. 1 degree and 0.5, 0.6 degree per 100 meters. Good. Is that clear to you? Now I start something, I will repeat the same again. I think your absorption capacity might be reached by now. Yeah? But then you have to think something. And you tomorrow morning, there might be rain, and you look out and you say, that's something I learned from Mr. Uhlenbrock last night. Now we look at precipitation. First is we look at convection. Many of you come from the tropics, but convection you have everywhere, even in the humid temperate climate. That's warm air rises due to energy input, then it cools, it forms clouds, and then it can even generate thunderstorms. So what is happening? You have near the ground surface, it's really terrible with this blackboard, but you see this is the ground, you can see that hopefully. Yeah? Sun brings in energy. What happens? Evaporation is happening. Yes, we discussed that today. But also the air is expanding. Yeah? If you heat something up, it's expanding. So you have also a rise of air masses up. When you have a vertical upwards movement of air masses, what happens? It gets cooler. Yeah? And as long as the humidity is not 100%, how much does it get cooler per 100 meters? 1 degree per 100 meters. So it's moving up. It rises. At a certain elevation, it reaches the dew point. It rises further. Now, not 1 degree per 100 meter anymore, but 0.5, 0.6 degree per 100 meters. And condensation is happening, so you produce clouds. Yeah? And if you have this vertical up movement of air, then you produce clouds, more and more clouds, higher, sometimes several kilometers high. Here you see a small cloud, small cumulus cloud, vertical extension, few kilometers, basically a very sharp condensation line here, that's the dew point line, in maybe 2 kilometers in this example, goes up to 6-7 kilometers and you have one cloud. Yeah? If you have more vertical rise of air masses, it can go further up. Huh? Not only 6 kilometers, up to 12 kilometers, and you see quite a significant vertical upwards movement of clouds. These things are quite mature stage of a cumulus nimbus cloud, and this up movement creates, from here we have drops and ice crystals. Vertical wind brings it up, but at some stage they get too large, too heavy, and then they fall down as ice or rain. Then the rain is melting and you have strong rainfall. This is a circle, you could say. Here upwards movement, very high, up to 10-12 kilometers, sometimes even higher, and very strong rain down here. Yeah. Then the whole thing can collapse also, and you have rain all over below the cloud, and you can have very heavy rainfall down here. Here are some examples. This is we call that the umbros. That's this big thing above the cloud. So here's the dew point elevation. You see that here. Vertical wind forcing air to move up, and then spreads out to the side, and usually the rain starts here then at the side of this convective cell. We call that this uprising of moist air masses convection. Some other examples, you see also very localized rainfall. You can have only maybe 1-2 kilometers, and I'm sure you all experienced that before. You drive or you walk and you see a cloud, you drive into it or you walk into it, and it was dry here, and 100 meters later heavy rain. Huh? Very sharp transition. Yeah? That's typical for convective small scale cells. Yeah. You also see this here, it starts raining there already. Here still, where the picture was taken, is nice sunny weather, and here very large extension of vertical clouds, up to 10 kilometers. This can be up to 10 kilometers or even more in the tropics, and very intense rainfall. Here's another example from Japan. Here it's raining cats and dogs, as we say, huh? And here it's dry. There's very localized rainfall. Yeah? And I'm sure you all have seen that before. Last slide for today. Though we talk about the generation of convective storms, this is due to vertical instability of the air, so vertical up movement of uprise of air, cooling, and then condensation and precipitation. The rainfall, the precipitation that can come out of this is rain or hail. Yeah, very intense rainfall. Hail I explain next on Friday. Very high intensity, can exceed even 40 millimeters per hour. This is really intense. It's really, you get absolutely wet. 40 millimeters an hour. That's very intense. Can be even up to 100 millimeters for a few minutes. Duration, we talk about short duration, so a couple of minutes, maybe hours, but not days. These convective cells, very intense, but then it's also over. I'm sure you experienced that as well. When you saw this convective thunderstorm, yeah, it was very intense rain, but maybe for an hour or two, and then it's over again. Atmosphere is clean again, empty, and you can have even sunshine again. So very, very intense, strong changes. The scale is a few kilometers. It's very common in the tropics. But also we observe that in the temperate zone here, in Holland even, yeah, can produce flash floods and is also accompanied by lightning. Is that clear? Yeah, so I promised the one person from Rwanda why it's raining so much in Holland. This could be one reason, but this is what only happens in the summer here. You have not seen this yet, I think. Yeah, it was not warm enough. But in the summer we can have these type of rainstorms. In all tropical countries you have these type of rainstorms as well, very often, yeah. And only on Friday I answer your question why we have so frequent rain in the Netherlands, because there are other rainfall generating mechanisms. But we do that on Friday.